Everyone has run low on gas before. Most likely you've had to gas up a car at least once. Gasoline is a part of our everyday lives. And what goes into making gasoline is a part of physical science and you. Let's talk about boiling point and pressure, and how the manufacturers of gasoline are concerned with it every day. This is one definition of boiling point and pressure.
Boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure of the atmosphere on the liquid.
Vapor pressure is related to the amount of kinetic energy within the liquid molecules. Before we find out why people who make gasoline would be concerned with boiling point and pressure, let's take a look at an experiment showing how pressure affects the temperature at which water boils.
Water boils at 100 degrees Celsius at sea level. You can see our barometer reads 29.9 inches of mercury, and the water is boiling at 100 degrees Celsius. Let's look at a model of the water being heated. The blower represents the heat being applied to the water. The moving particles represent steam, and the two red balls represent air at atmospheric pressure. As we turn up the blower, it represents a rise in temperature, which increases the evaporation rate. The steam detector measures the evaporation rate. The meter moves erratically between 20 and 30. This will represent the boiling point of water at atmospheric pressure. We will mark that point, which will calibrate our device, and we'll label it 100 degrees Celsius. Now let's go back to the real boiling water. We're going to reduce the atmosphere over the surface of the boiling water by removing the air with a vacuum pump. All of the water vapor coming off the pot is trapped in a chemical that absorbs water. The meter readings on the pot indicate that we have reduced the atmospheric pressure by 5 inches of mercury. The temperature of the boiling water is now 95 degrees Celsius. Back at our model, notice that one red ball is in position over the water, symbolizing the reduced atmospheric pressure due to the vacuum pump. The blower frequency is adjusted so the meter readings are again between 20 and 30. Note the position of the dial is at a lower setting, representing the lower temperature required for boiling. Let's see what happens if we increase the atmospheric pressure over the boiling water. First, we'll remove the vacuum pump and replace it with a small glass nozzle. The nozzle restricts the immediate release of the steam over the liquid. This tends to raise the pressure of the vapor over the liquid in a quasi-confined space. The boiling point is now 105 degrees Celsius. In our model, we now have 3 red balls over the water to symbolize the increase in atmospheric pressure caused by the glass nozzle. We again adjust the blower to the same readings between 20 and 30, but this time we have to increase the dial setting, which represents the higher temperature required for the water to boil. The pressure at 105 degrees Celsius can be estimated at 35 inches of mercury.
Now, let's relate these experiments to gasoline. Gasoline is refined from crude oil, which is recovered from oil-bearing formations beneath the Earth's surface. The crude oil is distilled and chemically modified to yield a large number of products.
Distillation of crude oil is accomplished in a tall device called a fractionating tower. The crude oil is vaporized by heating in the furnace. The heated oil is pumped into the fractionating tower. Once there, portions of the crude oil vapor form liquids which collect on trays in the tower. The hydrocarbons in the oil that are most volatile or have the lowest boiling point go farthest up the tower before condensing to form liquids. The trays upon which the liquids condense are arranged so that the heated vapors bubble up through the liquid in the trays. This gives an efficient separation of the crude oil into fractions based upon the temperatures at which the hydrocarbons boil. The refined products are pumped into large tanks as either a final product or stored for further refining.
Let's see some more examples of things concerned with boiling point.
This dry cleaning machine depends on distillation to reclaim and clean the expensive dry cleaning fluid so it can be used over again. The dirty fluid is heated to its boiling point. This turns it into a gas which is condensed back into a liquid and stored. When all of the fluid has been boiled away, the only thing left in the boiler is the dirt and soot that the fluid absorbed. The household pressure cooker also utilizes boiling point and pressure. As the evaporating vapor builds up under the lid of the pressure cooker, pressure upon the surface of the liquid is increased, which prevents boiling. This raises the boiling point of the water. The increased temperature of the boiling water cooks the food faster. Conversely, if the pressure over the water is reduced, the temperature at which boiling takes place is reduced.
What do you think would happen if pressure is reduced to the point of a vacuum? This causes special problems for the United States space program.
The NASA astronauts must use special spacesuits to protect themselves from the extremely hostile environment they work in. Space is a vacuum, and our experiment showed how less pressure means less heat is required for boiling. So liquids would boil instantly in outer space. The external pressure is so low that a liquid propellant, battery fluid, or human body fluid exposed to it would boil. Without the suit, the astronaut's blood would boil instantly. Boiling is actually evaporation taking place beneath the surface of a liquid. It forms bubbles of gas which are buoyed to the surface where they escape. The speed of the molecules forming gas must be great enough to exert as much pressure within the bubble as the atmosphere and water above exert. Therefore, boiling depends not only on temperature, but on pressure as well. More surface pressure means more heat will be required to boil. Less surface pressure means less heat will be required to boil. Let's take a look at our experiment again. Energy must be supplied for boiling to continue. This energy is absorbed by the liquid as it becomes a vapor. The energy promotes the conversion of molecules from the liquid to the gas phase. Spacing between the gas molecules is greater than that between water molecules. Here we reduce the atmosphere over the surface of the boiling water. Notice that one red ball is in position over the water, symbolizing the reduced atmospheric pressure. Now we increase the atmospheric pressure over the boiling water. Three red balls symbolize the increase in atmospheric pressure. The boiling point of glycerol is 290 degrees centigrade at standard atmospheric pressure of 29.9 inches of mercury. If we boiled this liquid in the same experiment instead of water, the temperatures would be different, but the results would be similar. Remember, crude oil is made up of many different chemical parts. Each of these parts has a different boiling point. During fractional distillation, how does the temperature vary as the crude oil travels up the tower?
Let's review that definition again.
Boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure of the atmosphere on the liquid.
After seeing the examples and how they relate to boiling point and pressure, the definition seems to make more sense now. So the next time you fill up with gas, think about how boiling point and pressure affect us. We're exposed to physical science laws every day and don't realize it. Try to see what these laws mean to us as we introduce you to the physical sciences.